Mhm. So, welcome to the 15th class, which was intended to be put on 6th Feb, but instead, much of this was discussed in class on 8th Feb. So, just as in class, I shall also spend some time telling about how statistical physics is done, or some of the topics of statistical physics in the modern context, in the soft matter and biological context. And of course, we'll be doing that more in the rest of the course. And the first half will be discussing some polymer physics, just to show that statistical physics is also used in other contexts beyond this ideal gas and magnetism and so on and so forth. These are things which are typically not discussed in the statistical physics one class, but I thought it's a good idea to spend some time to tell you about other things. So that will be recorded in part A of the 15th class, and then there'll be a part B, which will basically go on with the standard calculation of partition function for the ideal gas and other properties like equipartition theorem. Uh, so this is a slight detour, but we shall do it as we did it in class. What I want to tell you is that, there are, so what we have been discussing in terms of partition function is that there are systems which is in contact with a heat reservoir, and thereby it can explore different microstates for the canonical system, for the system which can exchange energy with the reservoir, and as a consequence, it can the system can have different values of energy, and for each values of energy, there can be different microstates. Now, uh, just to tell you about the kind of work that I do, I'll spend some time to tell you about a polymeric system. And here the polymer, so this is from my web page. In the web page, in the members section, there is some movies made by Shumesh Kurhati, who is a senior student. And here what we show is essentially a polymer which is taking various conformations in a background fluid which you can't see. And it's not explicitly modeled on as well. So before I tell a bit more about it, let me tell about how a physicist looks at a polymer. In class 11 and 12, of course, you have come across polymers which are chemical units which are repeated over an extremely long chain, identical copies of the chemical units which are repeated, right, like polyethylene or so on, and each chemical unit is attached by a single bond or a double bond uh, to the next chemical unit. And polymers are very useful for industry and so on and so forth. But what the polymer physicist or typical the statistical physicist looks at a polymer is something a bit different. So what polymer physicist or a statistical physicist would look a polymer as is one single object, say with 100 monomers, as you see here. Uh, so these are one object with multiple degrees of freedom. So in a gas particle, a single object, suppose the gas molecule or a gas atom, had position, three values of coordinates of position and three values of coordinates of momentum. Here, a single object has, if you say that the first monomer is specified by the position x1, y1, and z1, then the second monomer is at a fixed distance, approximately fixed distance away from the first monomer. They are connected by a spring, a harmonic spring, to the first monomer. So, since the distance from with respect to the first monomer is fixed, if you specify theta and phi. So you have x1, y1, z1, and the second monomer's position can be specified at a fixed distance L away from the first monomer, and if you specify theta and phi, you know the position of the second monomer. With respect to the second monomer, if you specify theta 2 and phi 2 of the third monomer, because it's at a fixed distance, the third monomer is at a fixed distance L from the second monomer, then you can specify the position of the third monomer, and so on and so forth. So basically, if a particle, if a chain has 100 monomers, then you can specify the position of all the monomers with three you need to specify x1, y1, z1 of the first monomer, and then 99 other monomers, you just have to specify theta and phi for each with respect to the previous one, and thereby the number of extra degrees of freedom is 2 into 99, because there are 99 other monomers. So this is in that sense an object with multiple degrees of freedom. And then you can have multiple polymers as well, and the question is, how does that interact with each other? Now this polymer with multiple degrees of freedom can take different conformations. So even suppose in this first snapshot, what you see, I've put all the monomers in a very ordered lattice configuration. There are 100 of those, 5 into 5. I think so, or maybe not. I mean, there are 100. So 1, 2, 3, 1, 2, 3, 4 into 6. There are certain, well, there are 100 monomers, I know, and they are in a relatively ordered configuration. And the idea is that each monomer is kicked around by other fluid molecules here. Now, the fluid molecules are not modeled explicitly, but rather by the so-called Lajva equation, which you shall learn after the mid-sem. So each monomer is feeling the effect of its other monomers. It's attached to an other monomer by uh, a spring of very high spring constant, so that the distance between the monomers is nearly fixed, but the spring can vibrate a bit, so it maintains the average distance of 1, say, so 1 unit of length, and uh, so the two monomers can fluctuate a bit about their mean position. Moreover, each monomer gets kicked around by the fluid, and the effect of the fluid is modeled by a friction force 6 pi eta r, which you might have done in your first class. The friction constant under certain circumstances, the friction constant is 6 pi eta r, and also a random kick force, which mimics uh, the effect of the fluid, the Brownian motion of a particle within a fluid. Because of this, each particle wants to move in random directions, but at the same time, they are constrained by the bond. So each particle, except the ends, are attached to two other monomers on its two sides. So while it wants to do its random motion, it is also constrained due to the forces that it feels due to the bond. As a consequence, what this polymer does is it takes very random configurations. It basically explores configurations space or conformation space. As you see, as time proceeds, the polymer chain does not remain in a compacted form, neither does it completely spread out. Instead, it takes various conformations, and these conformations in this case correspond to different microstates. So this polymer, so the energetics of these monomers are that if two monomers overlap with each other, there's a high energy cost, but if they don't overlap, there's no particular energy cost. They're held together by springs, and in terms of free energy, What is its equilibrium conformation? Its equilibrium conformation is decided by the minimization of free energy U minus Ts, where U has here relatively very small amount of contribution. On the other hand, depending upon the temperature, the system has an average entropy. Why an average entropy? Because the number of microstates that it can take, uh, it can fluctuate. I mean, if the monomers, if the end monomers are relatively close together, they can take a comparatively larger number of uh, microstates. This with a fixed end-to-end distance, uh, the the number of microstates this polymer can take is rather large. On the other hand, if the polymer was completely stretched, it could access only one microstate. It could have very minimal energy, but the number of microstates it could access is relatively less. So S would be less for that set of conditions. So what this system is doing is essentially, as the end-to-end distance is also changing, it is accessing different microstates, and polymer physics essentially um, con considers the statistical mechanics of initially a single polymer with multiple degrees of freedom. So how would it spread out? What would be its average size? What are the statistical quantities you can talk about? The density of monomers, what would it be, especially as n goes to infinity? And here it is, each polymer, each monomer can take higher velocities or lower velocities by taking energy from the thermostat. I mean, from the background fluid, which is not explicitly modeled, but modeled by the so-called Lagrange equation, uh, which so writing down this effective description, Einstein, of the Brownian motion of a particle, where the bath degrees of freedom are replaced by a friction term and a noise term, was first proposed by Einstein in 1905. So there is the Barth degree of freedom, which is not for which you are not writing down explicit equations of motion, but this effective bath is transferring energy or is absorbing energy from this polymer molecule, because of which it can take different conformations. And the statistical physics of one of these molecules, multiple a number of molecules, where the free energetic contribution mainly comes from entropy. The large number of conformations it can take is also considered the statistical physics of polymers. You can also consider, so that was a flexible polymer, so that the bonds along the contour could point in any direction as long as two monomers didn't overlap with each other. So it could point along any like this, but of course if it was exactly so-called 360-degree, the angle was 360-degree, then the monomers would overlap, so that those bonds are not allowed. Yes, but one can also consider, let's have a look at four chains, and let's look four flexible chains, and let's have a look at how they behave. So here what you have is basically different chains are colored differently. Call this purple and yellow and blue and red. So you have 400 monomers in a background bath of fluid particles where the fluid is not seen. There's an effective description of the background, and here you see each of these four chains are taking all possible conformations, and each particle is trying to do a Brownian motion. It is doing a Brownian motion, but in addition, there are constraints of bonds which by which they are attached to its neighboring monomers. And you see these polymers are trying to explore phase space. They are moving far apart. So if you had cut the bonds between these monomers, what you would guess is gas molecules. except that these are dilute gas molecules. If you had cut the bonds, they would move around in space, and only when they collide would they exchange momenta. Here, note that energy is not conserved. The velocity of each of these particles can be high or low and can exchange energy with the reservoir. But instead of showing ideal gas molecules, I'm showing you polymer chains. Now, the polymer chains themselves can collide. They can take different conformations. Here, they can also take different positions and so on and so forth, right? So here energetics is hardly playing a role except when monomers overlap with each other. On the other hand, you could also have semi-flexible chains like this. So here you have an energy cost for bending. So here this chain is also taking all possible conformations which are allowed. But here in the F equal to F stands for free energy, U minus Ts, there is also contribution from the bending energy. So if there are very sharp turns, bending energy would be, so there would be very high bending energy, and free energy would not be minimized. So this polymer is also taking all possible conformations where very high energy conformations are penalized. The probability of having very high energy conformations would be penalized. So microstates in which there are extremely sharp bends along the chain contour, they will be accessible with the probability e to the power minus beta EI, where EI is the energy of that a particular conformation. That would be one particular microstate. Yes, but most of the time the system would bend a bit, but not much. And given the constraint of high bending energies, I mean, of course, it can rarely access very sharp conformations. Here, what this chain would do is access all possible conformations, minimizing its free energy. So, number of conformations in that sense is a bit decreased because the free energy state would correspond to the conformations that it can take without costing high uh, without high energy cost for bending. So you see that over as you go along the length of the chain, over a certain length, yes, you do see some bending, but if you look over relatively short chains, I mean lengths of chain or segments of chain, they are relatively straight. But over large distances, they do in fact bend, but each angular bend is relatively small. So the if you take three monomers, the angle between them is close to 180 degree as sharp bends are penalized. So this polymer tries to take all possible conformations, tries to increase its number of microstates, but the more probable microstates are those microstates less which have less energy of bending. Of course, this chain would be energetically most happy if if this polymer was completely straight, right? If it was perfectly straight, then the number energetically from the energy of bending, it would have the least energy. But that would not be necessarily the least free energy, because at times the system can take energy from the path, get into a slightly higher energy state, which will allow it to take larger number of microstates. Remember what we studied in the class, that the system can take a certain amount of energy depending upon the temperature T and can access higher energy microstates, uh, and it will be decided what will be its average energy depending upon the number of microstates. I mean, how much energy to take will depend upon the number of microstates of the bath, but the product, the entire system, uh, will have the maximum entropy. So when you're talking of the entire system, you're talking about the entropy of the entire system. But when you're talking about this particular chain, you're talking about the free energy of the chain, where the bath is at a fixed temperature. So this system in contact, the smaller system in contact with the heat reservoir, we're going to talk about minimization of free energy of the smaller system. But for the bigger system, this system plus bath, you are going to talk about the maximum entropy of that full system considered isolated. Considered isolated, right? But so what this system, the smaller system in contact with the heat reservoir, what it is doing is it has taken some energy from the reservoir, which allows it to explore larger number of microstates, which will minimize its free energy. If the temperature of the reservoir was increased, then this system would take on an average more energy than it currently has, which will allow it to explore larger number of microstates. So this system's equilibrium conformations, or average minimum equilibrium conformations. Why average? Because the energy of this system is fluctuating. Sometimes it has slightly higher energy, sometimes it has lower energy. Depending upon how much energy it has, it can take different amount of conformations. So this system actually has an average energy, and then the way its average energy is decided is depends upon the temperature, because if the temperature of the bath is more, this system can access even higher amount of energy, which will also allow it to explore larger number of conformations. But for a fixed temperature, the way the average value of the energy and the number of conformations, the average number of conformations corresponding to entropy it can access, depends upon the temperature of the heat reservoir, and that decides the state of the minimum free energy. Here you might have seen that sometimes you're getting this set of chain. It is not an additional chain. It is just that this polymer chain has crossed this boundary and entering this wall from the other end. You will see that in your in a computational physics course. So here you have periodic boundary conditions at the walls, right? So this is how the what I want to say is, this is how um, statistical mechanics is acting. This is, here you see where energy, you have one particle, I mean you have one chain, multiple degrees of freedom, but through one system, one chain, you can, I hope, I could help you to visualize how the system can absorb energy, access higher energy microstates, and thereby have larger number of conformations, larger number of microstates, as it can do fluctuations. So that's what I have been trying to explain to you. Now I can also show you semi-flexible polymers with 100 monomers, bending energy something, where you have 4 chains, and so again I had kept the chains initially at time t equal to 0. These are simulations by Stromesh Kurati. So I had just supervised it. So these are chains, 4 chains. I had kept them compact, but if I kept them compact, then I mean, first of all, it costs very high amount of energy because there are sharp bends in the chain. So it tries to spread out, and it not only tries to spread out and take different conformations, it also tries to avoid each other, because then it will have the it can take more number of conformations. So that's what you are seeing essentially, except that instead of one chain, now you can see 4 chains. You can have also other quantities. I think I have some ring polymers. Ring polymers, yeah, conformations of 4 ring polymers. So here these are flexible chains. Here they are uh, flexible chains, but the end of the each polymer chain. So monomer number 1 and monomer number, I don't know, they might have 100 monomers or maybe 200, I don't remember. Uh, but the last monomer is attached to the first monomer, so it forms a ring. And these ring polymers have very interesting properties. So they try to avoid each other and they try to repel each other to increase its entropy. And you see that the chains are hardly interpenetrating, if you have noticed that. And that in confinement can be made to show interesting properties. I'll spend 5 more minutes discussing a few other properties which I had discussed in class. So I had used ring polymer dynamics. Now, we go into my research page. If you go down, I have somewhere, yes, I think bacterial DNA replication and segregation by Debashmitra. So this simulations is supposed to model the segregation of so since I have a bit more time and you're free enough to see this, I'll spend some more time to tell. I'll give you a background as well. So I have used the polymer properties to study some organization of the DNA polymer in bacteria, and their question is that there is no dedicated so you know this one of the simplest cell is the so-called E. coli bacteria, and this looks like this cylinder. It's cylinder with spherical caps, if you like. So these are E. coli bacteria inside which there are long chains and they are highly packed. And one looks at uh, this DNA. The physicist looks at these DNAs as polymers, and the broad issue is that whenever a cell wants to divide, and here you see that a cell, an E. coli cell, has made a copy of itself and it is about to divide here. So whenever it wants to divide, the DNA has to be replicated, and not only after it has to be replicated, they have to be faithfully segregated to two different cells, so that the cell division can the mother cell can divide in the middle and produce two daughter cells. So the point is, these are extremely long chains. So one has the E. coli cell has around 4.6 million base pairs. So another chain has to be made with another 4.6 million base pairs, and these two chains have to be segregated, and they would like to entangle and so on and so forth, but they have to be compacted, segregated, and put into two different cells in a finite amount of time for these cells to separate and for cell division to take place. Now, just to give you an idea, 6.4 million base pairs, if you put them end to end, each base pair is around, I think, 3 angstroms or even less. So basically, in I think in around 2 or 3 nanometers, you have 11 base pairs. And so if you have 4.6 billion million base pairs. That's essentially talking about around 2 microns, sorry, 2 millimeters. And this cell is 2.5 microns in length, that is 1000 times smaller. So a 2 millimeter chain has to be compacted and put inside such a cell. And moreover, this cell has this DNA has to be copied and segregated to two different halves of the mother cell before cell division can take place. Now, for higher organisms, there are complex protein machinery to segregate the DNAs into two cell halves, but in bacterial cells, there isn't any dedicated machinery, such protein machinery to segregate the DNAs once they are replicated. And what was proposed is that the bacterial cell uses entropy, among other things, to segregate its DNA into two halves of the cell. Just to give you a background in 5 minutes, I want to tell you that bacterial DNA is a ring polymer. It's a ring polymer of the kind that I was showing you in the movies just before. The replication starts from a point. The origin of replication is called the ori. So this point, so some protein comes here, makes a copy of the base pairs which are here, so that this ori, there are two copies like this, right? And this replication machinery, so once it has made two copies of the ori, this replication machinery marked in blue here and here, these two, there are two replication machineries, protein machineries, and they basically travel along the length of the contour of the DNA polymer, and this one travels along the length of the contour of this DNA polymer to meet here at this point. It terminates the replication at the so-called ter. Ter for termination. This is the termination point. So this is called the replication bubble, and the protein machinery, wherever it sits and makes copies, it does the replication process. So this is called the replication fork, because from here, you have the first ori and the second ori, and these are oris of the daughter DNAs. This is the mother. This is the mother. And these replication forks, the protein machinery, wherever it sits along the mother's chain contour of the mother, that travels along this and it travels along this, and the replication bubble becomes bigger and bigger, so that at the end of it, you have two full chains, two full ring polymers attached at the ter. Now, here you see that this is shown as a circle, but this is a schematic diagram. The polymers, because they have entropy, because they want to take all possible microstates, they are more of the kind that I showed you in the movies. So they are not such perfect rings. And uh, yeah, I mean, they are, DNA is rigid, but that's only at the nanometer length scale. But when you're talking about 6.4 billion base pairs, length scales above, say, around 50 nanometers, or around more than 150 base pairs. If you look at length scales larger than that, just like I showed you the semi-flexible polymer, over a long distance, they look like a flexible polymer. So similarly, over long length scales, they are flexible, especially at the micron length scales. Above 50 nanometers or 100 nanometers, they become flexible. So basically, this won't be this perfect circle. Instead, it will be an entangled zoo, right? And the question is, how is it that this part, this ring polymer, will occupy one half? This is one daughter, and this is the other daughter, and this will occupy the other half, and they are conjoined at the ter, and this ter crosslink, or this ter link, is cut just before cell division. So the mechanism was proposed by Yongren, Sukjunjun, and but they did something else, but this figure is from there. But it was suggested using polymer models of DNA by Sukjun, Bella Mulder, and Wright, that basically any two ring polymers, if you put them overlapping in and under tight confinement inside a cylinder, the tight, the focus on the word tight is important. It has to be really tightly confined. Then two ring polymers, DNA of bacteria are ring polymers. Uh, they would segregate to two halves of the cylinder to maximize its entropy. The entire idea is that if two ring polymers occupy two different halves of the cylinder, the number of conformations they will be able to take is more. And so what it is shown here is suppose a schematic diagram. I mean, this is, I think, from the simulations actually of these folks, that this is essentially the mother DNA. This is the mother DNA, and this mother DNA, from there you are getting the the monomers or the DNA polymer of daughter number 1 and daughter number 2. So the mother DNA is being replicated to produce daughter number 1 and daughter number 2, and the length of the mother decreases. The length of the mother DNA decreases as the replication fork moves around this arm and around this arm, and thereby you see that more and more red colored monomers corresponding to daughter 1 and blue colored monomers corresponding to daughter 2. Of course, this label red and blue is just so that you can and I can see it. These are just labeled, they're just colored for ease of visualization, and anyway this is from a simulation. And note that yeah, so if you just had two ring polymers without doing any of the biology, so you take any ring polymer under high confinement, put them in an overlapping state, they would spontaneously segregate to two halves of the cylinder, just like this and like this, right? And one doesn't need to do anything. So I have solved some other more uh, intricate models. There were some other problems that this ring polymer doesn't explain, that certain particular segments of the DNA occupy very particular positions along the cylinder as the cell divides. Now, how that happens was not explained, so I have used some other ideas. But just to show how this process takes place, without going into the details, what I'm going to show here. So what you have is a cylinder in which there is a chain, blue chain here, and these red points correspond to the ori which first gets replicated, and you see some pink monomers that corresponds to chains of the replicated, another copy of the DNA which is being created. This yellow is the ter where the replication ends, right? And what you'll see is that I'm a physicist. I don't know. I mean, I don't know any biology. I've not put here any uh, proteins or whatever. I have used some crosslinks and entropy principles. And what you will see at the end, that as the simulation goes on, this cylinder will elongate, which corresponds to elongation of the cell. And moreover, you will see more and more pink monomers appearing. These monomers are appearing because replication is going on, and moreover, you can see that the length of the cylinder is increasing. And what I expect you to see is, towards the end of the simulation, uh, there's a pink polymer which will have around 500 monomers, just like the blue polymers. They will occupy one half of the cell, and the blue polymer will occupy the other half of the cylinder. And this has been done without application of any external force. This happens automatically, spontaneously is the word. The spontaneous organization, that the pink you see is occupying this part of the cylinder, and the blue is occupying this a part of the cylinder, happens automatically by these two chains, because if they are segregated into two different halves, then they will have more entropy. Moreover, you can see that this yellow ter automatically occupies the middle of the cell because it is joining the two, the pink and the blue polymer. And that is exactly what is seen in experiments also, that the ter occupies the middle of the cell. And this can absolutely self-emerge. The key word is self-emerge as a consequence of entropy, right? So you see, I mean, the thesis is the way physicists are looking at biological systems. They're proposing that in some cases, not always, of course, these are driven, there are many driven aspects also, which I have not talked about, but biological systems can harness entropic forces or entropic effects to organize itself within the cell. In this case, to divide its daughter DNAs or to segregate its daughter DNAs to two different halves of the cell, uh, such that cell division can take place. With this, I shall stop recording here and go over to the other part, which